that's just a little bit of a visual about what we're doing. Here's another, again, really short. This is from Khan Academy.
All right, the basics of a spectrophotometer. So first of all, you're going to have a light source, and the light is going to shine through usually a lens or something that condenses the light, and it will go through an entrance slit into this chamber that contains a monochromator. So this can be a prism, like represented here, or it can be a diffraction grating of some sort. The idea of a monochromator is it splits the light into mono, one color, so beams of a single color. That's monochromator. So this prism will take this beam of light and split it into different colors and different wavelengths of the electromagnetic spectrum. And then you have an exit slit, and this can be moved up and down to select whichever wavelength that is appropriate for the sample being analyzed. So here we have green coming through, and so we've selected green, and so this green part of the light is going to come through and hit our sample here, sample cuvette, and then our sample cuvette has sample in it at a set concentration, and so some of this light is going to be absorbed by the sample, and the rest of it's going to be transmitted onto the photodetector. So the photodetector's job is to detect the amount of light that's been transmitted through the sample cuvette, and its job is to convert this electromagnetic radiation, EMR, or light wavelength. It is going to convert it into an electrical signal, into electrons, and that's going to be transmitted to a readout, and it will give you the number of the absorbance for the readouts here.
Okay, so again, kind of the same thing, and that's probably doesn't make a lot of sense, but hopefully it makes a little bit of sense on what's going to work. And you guys will see this instrument tomorrow, and it's nothing that earth-shattering, but this is again what kind of the logic of how we're going to do this. So a couple things. So if you've got that handout in front of you, first of all, let me kind of coach you on a couple things here. If you look at, so you got the title, the purpose, the problem. I think reading the background is really a good idea. The procedure on the back of the first page or the second page, I'm going to do that. I'm going to do that tomorrow. I've actually already done part of it. If you look on pre-lab question 1, that's the reaction we're going to use. So I'll let you guys write that out. You guys can write that out. And number 2, you'll see me do the lab. But number 3, so this kind of goes along with what I was just trying to talk about. So what you'll see tomorrow is number 3, the copper 2 ions appear as blue. You'll see that tomorrow. This is the transmitted color. Okay, so that's the color that's not absorbed. The wavelengths of the light that are not absorbed give rise to the perceived or transmitted color of a substance. So what's absorbed is the opposite of what's transmitted. So it says, based on the principle of complementary colors, which colors or wavelengths of light would you expect to be most strongly absorbed? So not what's transmitted. So blue is there on that wheel here on the bottom. So blue is down here on the bottom. That's what's transmitted. They're asking us what then is absorbed. Well, it would be what's on top. So really, the best answer would just be orange, and you guys can answer this right now, or red, orange, yellow. So a number 3 on pre-lab, the red, orange, yellow, especially the orange, is going to be the most highly absorbed. And when we set the wavelengths, we're going to set the wavelengths for the one that gives the highest absorbance. Okay, and then if you look on this page here, I've given you data. Okay, so I've given you data. So I did 2 solutions. I did the copper nitrate, and I did iron 2 nitrate. And so what you're going to do, so right here, so you've already got this data done. So you're just going to make a graph, and the graph is going to look like this. It's going to be put absorbance on the y-axis, put wavelength on this axis, and make the graph as big as you can. And just make a line graph. just make a line graph. So this first graph here on number 1, this will be for the copper nitrate. And then if you look on this page, this graph will be a second graph, and this graph will be the same thing. It'll be absorbance, and it'll be the wavelength, and this will be for the iron nitrate. And again, all you're gonna do is plot the points and make the graph. And then it says the lambda max. Well, remember, wavelength is lambda. So wherever it peaks, that's the lambda max. That's the maximum wavelength. Or that's the wavelength that's giving the maximum absorbance, which again, that's not the color we observe, that's the color that's being absorbed. So you guys can do that one. And then the last one that I'll talk about today, and I want to talk about just 2 other things with the lab. If you look at the very last page, it's kind of worded in a weird way. So the very last page, number 2, it says this: the characteristic flame test colors of metal ions. And flame tests, and hopefully you remember, and I think I showed you guys even a YouTube video this year of flame tests where like potassium's purple, copper is blue, I think strontium's red, but are due to atomic emission spectra. So that's the lines, the wavelengths that are given off. Discuss the relationship between the absorption and the emission of light and the factors responsible for flame test colors. Okay, all this is all I want you to do. So let's just do this one right now. Let's just make bullet point, bullet point, bullet point. This is what happens. Let's answer number 2 right now.
Mr. Wood, where is that question?
It's on the very last page, Rex. It says
Okay.
characteristic flame test colors. So this is asking what's causing the colors of the flame test. So when we're not going to use what they say quantize and Planck's level, let's just do this. So step 1, electrons are in the ground state. Electrons are in the ground state. Step 2, electrons absorb energy. Step 3, the electrons are in the excited state. Okay, so the electrons start in the ground state, they absorb energy, they go to higher energy states, the excited state, but the electrons are not stable there, they don't stay there. So then the electrons return to the ground state, but when they do that, so after being in the excited state, then the electrons release energy, returning to the ground state. So electrons release energy and they end up back in the ground state. That released energy is light. And that's what we observe when we did the flame test or we did the spectral analysis test. Okay, and they have us actually do, and really this lab is kind of a review of things that we did in chapter 7. Okay, I want to talk about one other thing. Anything on up to this point on that stuff? Okay, so let me just talk again, and I'll come back and we'll look at this more. And this is not going to be due until a week from Friday. We're going to do it tomorrow. But what we're going to do is I'm going to make up, I think it's again, copper nitrate of 4 different concentrations. Okay, and what we're going to do, and we're going to put them in this spectrophotometer, which I'll show you guys tomorrow, and we're going to measure the absorbance. So we're all going to have the same data, and then we're going to do a graph. We're going to do absorbance versus concentrations. This graph, instead of wavelength, is going to be concentration. But if we go back to Beer's law, this is going to be a linear relationship. So as concentration increases, absorbance increases. It kind of makes sense. The more more concentrated a solution is, it's going to be able to absorb more light. So we're going to get pretty close, hopefully, to a linear relationship. Okay, so it'll look like this. And then I'm going to show you the reaction I'm going to do. It's a reaction. Again, I wish that you guys could actually see it, but we'll do the best we can. I'll show you. You have to do it in the hood because it gives off a toxic gas, and I'll show it to you tomorrow. Nitrogen is nitrogen dioxide. So I'll do it in the hood, but I'll show it to you just so you can see it on the Google Meet. But then I'll take, after the reaction, I'll follow the directions, and what we'll do is that we'll then measure the absorbance of that solution, because the copper will react with the nitric acid. And here is going to be from the brass. We'll measure the absorbance. Well, if I know so these points here will be the knowns. These we'll know the concentration of. But this will be the unknown. We don't know that. We know, but we can measure the absorbance with the spectrophotometer. Well, we go over here and down here, and then we'll know the concentration. And if we know the concentration, the molarity, we'll know the volume. So we can find the moles of the copper, and then we'll know the total mass of the brass, and we'll find the percent. So again, that probably makes no sense at all right now, but hopefully it'll make more sense as we go through. So, okay, I want to move on then. I do have a good joke for you guys today, so I'll laugh at myself as I tell it. But anything on the lab right now, and obviously we need to do lab, and it's new stuff and it's confusing, but anything on that right now, anything we didn't get? Okay, so back to, and I did present a lesson yesterday, and hopefully you guys watched it, but I do want to review a couple of the kind of the key points. And actually one thing that I actually want to go back a little bit to one thing that I use, and for those of you that have taken AP Bio with Miss Daly or Miss Dreesen, you guys, I know Miss, and I use the same guy, Miss Dreesen kind of got me onto this guy. He's the Boseman, Montana guy. Okay, but back to this page right here. There's a guy, and if you guys have not taken AP Bio with Miss Dreesen or Miss Daly, he's got, if you just Google Boseman Science, this might be a good kind of overview of kind of what we talked about with ionic compounds. Can you guys see this right up here? I think you can.
Yeah, we can.
Good. But what the Boseman Science guy does, and I would refer to him, now we're in the second semester, we're still months away from the AP test, but heck, you could even find what I just talked about, Beer's Law. And he does these little connecting diagrams, which are kind of helpful. But I just wanted to take a minute just to kind of review. Today we're going to review dots and kind of move into more covalent compounds. But this was just something that came from him, Boseman Science, which again I would recommend as we're going now into the second semester of AP Chemistry. But he does this, I think, a good kind of just how everything's connected. But we talked about ionic bonding. This is when we have a metal and a nonmetal. It consists of ions. Positive ions, which are called cations, and negative ions, which are anions. Remember, I always remember cations. The third letter in cations is a T, a lowercase t, kind of looks like a positive symbol. And cations, remember, lose electrons. And then anions, a negative ion, are negative, and that's when electrons are gained. But what we talked about on Tuesday, ionic solids are that thing Coulombic attraction or lattice energy. And what we said was, the larger charge difference or the smaller ion size give a stronger charge. And the stronger or a stronger Coulombic attraction or a higher lattice energy. So I just thought that was kind of a helpful kind of analysis review of stuff we talked about with ionic compounds. So, and once in a while I kind of go back and use his stuff. I went through, I think he's got 74 videos, and they're not that long. They're like, I don't know, 6 to 10 minutes long. But again, if there's something that we're doing that's kind of confusing, that would be a good reference point, Boseman Science. Okay, so I'm going to go ahead then. Are we good? Okay, so what I talked about then, what I talked about in our lesson yesterday I wanted to spend a minute on it. If you haven't watched it, it's linked up on my calendar just like it always has been. And I would recommend to watch it. But I do, when I post those things, I always want to kind of come back and just spend a couple minutes. So what this is here, and this I actually changed. So this is not online. I've changed at the bottom part of this, but we're going to do a ton of dots. We'll do a little bit today. We're going to do a whole bunch really through the rest of the month. And how we do dots are going to determine how we do shapes. And sometimes we can do the easy way, but not always. And some of these bigger molecules, these polyatomic ions that we're going to look at, we need to go back and we need to do it this way. So a major shortcoming of Lewis structures is the inability to predict molecular geometry. That means shape and many properties. So once we know the shape and we know the polarity, we can figure out melting point, boiling point, the types of reactions. And again, geometry always means shape. And so everything's driven by this thing called the Vesper Theory, valence shell electron pair repulsion. The idea is that opposites attract and likes repel. And so when molecules are taking their shape, the idea is the electrons repel from each other. They get as far away from each other as they can. And double and triple bonds are treated as one single repulsive cloud. We're going to talk more about those when we get into shapes. But here's the steps, and I want to do a couple today, and again, I'm going to do a bunch in the next couple of weeks of our class. But notice what I said there first in parentheses. If just matching up the single dots doesn't work.
Mr. Wood, are you supposed to be presenting? I can't see your screen.
Can you guys not see my screen?
Yeah, you're not presenting.
Oh, gosh. Sorry. Sorry, guys. Thanks. See, you guys need to. Oh, gosh. Yeah, when something's going haywire, let me know because Can you see it now, Rex?
Yep.
Okay. Okay, so kind of the key thing in this slide is what's on the bottom. So I'll give you guys a minute to copy that down. Yep, sorry about that. But when that happens, you guys let me know because I screw that up. Here's my joke while you guys, for those that are copying this down, it's one of my more favorites. An Irishman, a Mexican guy, and a New England Patriot fan, even though they're not in the playoffs, were doing construction, working on scaffolding on the 20th floor of a building. They were eating lunch, and the Irishman said, corned beef and cabbage. If I get corned beef and cabbage one more time for lunch, I'm going to jump off this building. He was sick of corned beef and cabbage. The Mexican guy opened up his lunchbox and exclaimed, burritos again. If I get burritos one more time, I'm going to jump off the building too. The New England Patriot fan opened up his lunch and said, bologna again. If I get bologna one more time, I'm going to jump off the building too. Well, the next day, the Irishman opened up his lunchbox. He saw corned beef and cabbage, and so he jumped to his death. Can you believe it? He jumped to his death because of his lunch. The Mexican guy opened up his lunch, saw a burrito again. He jumped to his death. The New England Patriot fan guy opened up his lunch, saw the bologna, and jumped to his death as well. Well, at the funeral, the Irishman's wife was weeping, and she said, if I'd known how really tired he was of corned beef and cabbage, I would never have given it to him again. The Mexican guy's wife was also weeping, and she said, I would have given him tacos or enchiladas. I didn't realize how much he hated burritos. Everyone turned and stared to look at the New England Patriot fan's wife, and the New England Patriot fan's wife said, don't look at me. He made his own lunch. That's it. That's all I got. Okay, so the bottom part, and I want to do a couple of examples, but the first thing we're going to do, this is for more advanced dots. We're going to count the total number of valence electrons. Number two, the central atom is always going to be the one that's written first. So everything's going to revolve around whatever's written first. And then you're going to, number three, you're going to put the other elements around the central atom, and you're going to fill each atom's octets, which means you're going to give everything 8. And the one exception that always comes up other than hydrogen. Hydrogen will have 2. And then kind of the key thing, which again we'll do a lot, the extra electrons, or if electrons need to be removed, they will come off or be added to the central atom. Okay, and again, I want to do a couple of examples here today. So I'm going to move on. Okay, is it okay to move on here? Okay, I'm not hearing any objections. Okay, so let me go back then. This was a slide that I did, again, on the lesson yesterday. So again, I want to kind of go through this quick. But I did the dot structures. I reviewed the dot structures for some that we have done that we can just do the old-fashioned way, just this way right here. And I'll review a couple of those. In the old way, the first year chemistry way is just where you do the dot structures, you connect the single dots. But the last 2 are advanced, and that's what we're going to get into in our class. So polyatomic ions, bigger molecules, we're going to have to go back and we're going to have to use the technique I was just talking about. Okay, so I want to do, so again, I did this on the lesson yesterday. Okay, so I want to do a couple of these on the board. Okay, so again, and I know probably a lot of you watched the video yesterday, and if you did, just be patient with me. I'm going to go through this fairly quickly. But if we go back and like H2, so this is the old-fashioned way, and if doing the single dots works, then we're going to use that. So H2, so here's the way in first year chem, hydrogen and hydrogen, each with 1 valence electron, and all we did is we paired up the single dots. And the thing that's going to happen in our class is that's not always going to work. So then the next one that I did was NCl3. Okay, so again, this one, especially in elements in the first and second row, you can really do it kind of the old-fashioned way. So the old-fashioned way, which is just the valence electrons, N has 5, chlorine has 7, and there's 3 of them. And then all we do is pair up the single dots. But that's not always going to work in our class anymore. So it looks like this. This is the way I would draw it. Mr. Hodis is going nuts over there. Okay, so then I did this one in class yesterday. I did nitrate ions. Let me just work through nitrate ion, and then we do carbonate ion. So here's dots, and then we're going to come back and again do a whole bunch of dots in the rest of the month. So this is now the new technique that I was just talking about. So number 1 is you count the valence electrons. So nitrogen is 5, oxygen is 6, and there's 3 of them. So 6 times 3 is 18, and then hydrogen is 1. 23, so that means I get 24 total dots. So I count the valence electrons. Okay, then I put the element written first in the middle, and I connect the other elements to it. Count the valence electrons, the element first in the formula is in the middle, the other elements around it, and now I fill everything's octet, which means everything gets 8. That includes the central atom. Okay, so valence electrons, the first element in the middle, all the other elements around it, fill the octet. Now I count. So I have 2, 4, 6, 8. That's a pair. 10, 12, 14, 16, 18, 20, 22, 24, 26. So I have 26 dots, but I said I could only have 24. So that means I got to take 2 dots away. And this is where I'm saying, in this case, I need to remove dots. So if we have to remove or add dots, we always do that off the central atom. So I'm going to take 2 dots off there. And if I leave it at this point, it doesn't work because the oxygens are all fine. They're all stable. They all have their outer shell filled, but N does not. And so what happens here is, and it doesn't matter which oxygen, and again, I'm going through this quickly. I did this on yesterday's video, but whichever oxygen, I chose this one, I think, and I could have chosen the one on the bottom or the one on the left, donates a pair of electrons. So what we end up with then is this. And actually, the way they always do it in chemistry is they always draw it with the parentheses. And you can really draw that again. If you go back and look at my video from yesterday, you can see I can actually do that 3 different ways. Okay, so let me do this one. CO3 -2. So here's carbonate ion. So the first thing that I do is I count the valence electrons. So carbon is 4. This one I did not do on the video yesterday. So oxygen is 6. So 6 times 3 is 18. 6 times 3 is 18. And -2 means there's 2 more. So that means I get 24 total dots. Okay, so then I put carbon in the middle. And I put the other elements around it. Okay, and then I fill the octet of everything. Okay, so now I count up. I get 24. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. This one's a lot like the last one. So again, I got 26 dots. I can only have 24. So I've got to remove 2 dots. And again, removing or adding are always off the central atom, so I remove there. And now I'm in the same predicament I was on nitrate. And it really doesn't matter which oxygen I choose. So I'm just going to start off with this one. So this oxygen, because right now, carbon does not have its outer shell filled. And so one of the oxygens has got to donate both. That's called a coordinate covalent bond. And so what we end up with then is this. Make sure you guys can see this. So what I end up with then is carbon, the double bond with this oxygen, the oxygen over here on the left. And again, that is one way to write carbonate. But when you can write something in more than one way, they call that resonance. So you could say, well, Mr. Wood, how about, why didn't you choose the oxygen on the bottom? Well, I could have. And so then it would have looked like this in terms of giving the electrons for the double bond. And again, these are all, it's called resonance. It's when you can write correctly the electron dot structure in more than one way. And then you could say, well, why don't you choose the oxygen on the right? Well, I could have. So here's another way I could have drawn that. Okay, and all these are equal. They're called resonance. But this is the way we're going to do dots on some of these bigger molecules that we're going to do. So, and again, that's, I want to keep going here, but just with dots. Okay, I want to go through a couple slides here. Okay, so we just did this slide. Okay, and all this diagram shows, it just shows the concept of covalent bonding, of where electrons are shared, is all that's going on there. This is a table. This might be worth writing this down. Electronegativity. We actually talked about this before vacation, and this was I think on the chapter 7 test. But what electronegativity is, it's the ability of an atom to attract and hold an electron. So it's the attraction an element has for electrons. And then the question there, what is the trend for increasing ionization energy? It's exactly the same. The trend for electronegativity is the same as the trend for ionization energy. So the trend, now there are different definitions. Ionization energy is the energy required to remove an electron, where electronegativity is the ability to attract an electron. But the trend is the same. The elements upper right have a larger electronegativity value. And I really like this periodic table because, and something to note here, and is when in first year chem, you guys were given this, and to decide if something was ionic or polar or nonpolar, you subtracted the elements. We said if it was greater than 1.7, it was ionic. If it was 0.3 to 1.7, it was polar. And if it was 0 to 0.2, it was nonpolar. They don't give us the periodic table in AP Chem. So this you should know. This you should know. It's an ionic bond if it's a metal and a nonmetal. Simple rule. It's an ionic bond if it's a metal and a nonmetal. Okay, it is a covalent bond if it's two nonmetals. It's a covalent bond if it's two nonmetals. And the reason I kind of like this periodic table, because the elements NOF and Cl are in the upper right and they are purple. And so this is what a polar covalent bond is. A polar covalent bond is when one of the nonmetals is NOF or Cl with another nonmetal. So what I'm saying is that this is our rule, because we're not going to have the electronegativity table. If we have NOF or Cl with any other nonmetal, it is polar covalent. And really, we should say F with any nonmetal, because it's so electronegative. So electronegative is polar. So if we have two nonmetals that are not from the NOF or Cl, that's nonpolar. And the best example of that is C and H. Okay, so this slide kind of goes over this. So the third type of intermolecular bond is called polar covalent. This is a form between atoms with somewhat different electronegativity so that a charge separation occurs. So again, let me say that again. So if we've got metal, nonmetal, ionic, metal, nonmetal, ionic, it's covalent if it's two nonmetals, but it's polar covalent if one of those two nonmetals is NOF or Cl. Kind of that upper purple, that very upper right side of the periodic table. So then in that little continuum, it says most covalent and most polar covalent. So let's just review what I just said. So H connected to H, those are two nonmetals. Whenever, and this includes NOF or Cl, whenever something is connected to itself, it's got to be nonpolar covalent. Okay, the second one, S connected to H. These are both nonmetals, and they're not from the NOF or Cl. So that's going to be nonpolar covalent. But then HCl, okay, so there's one of those four elements with another nonmetal. That would be polar covalent. And it's really good just to remember, F is the most electronegative, so it's going to make the most polar covalent. And then O is the second. So then the OH and the FH would be more polar covalent. A term that they use in AP is they use the term dipole moment. Dipole moment, you should know that just simply means polar, how polar something is. Okay, this slide, I'll just go through quickly. This is not a key thing at all. There are some problems there on the bottom, 19, 21, 23, that you guys can be working on. But 50% ionic character or greater is considered ionic. We're going to use the rules I said. Metal, non-metal is ionic. LiF is the most ionic substance known. The one that's always confusing in first year chem is HF, and I always let my students in first year chem, because if you use the electronegativity table and you subtract 4 minus 2.1 is 1.9, it's ionic, but technically it is very polar covalent. And that's why the rules we have, where we have two nonmetals and one of those nonmetals is that upper right-hand section, it's very polar covalent. Okay, I'm going to skip this page. We have already done oxidation numbers, and this is the page I want to finish with today. This thing called formal charge. So I'm going to give you guys a minute to write this down, and I'd like to do an example here and give you one to work on for next class. Okay, this thing called formal charge, and this, they lied to me years ago. They said that this would not be on the AP chemistry test, and sure enough, it was. And so this might be something, and I didn't tell my period 2 class, but it might be worth writing on your formula sheet somewhere, just in case. FC, formal charge. It's used to determine whether one Lewis structure is more likely than another. And this is the equation I use, which is a little bit different than some people do it. But formal charge is equal to the number of valence electrons minus the assigned electrons. And I'm going to go through this quickly as I'm running out of time, but what an assigned electron is, but I want to do a couple of examples. For a single bond, it is 1. For a double bond, it is 2. For a triple bond, it is 3. I'll show you what I mean. Structures with larger formal charges are less likely than those with small. So the whole point of formal charges are when we have 2 possible Lewis dot structures, which one is the more likely one? It's the one with the lower formal charge. An element with a high electron negativity is more likely than one with a negative formal charge. Okay, and here on the bottom, I'm going to, can you guys see that?
You stopped sharing, so.
Okay. Tell you what, I wanted to anyways. Okay, so here is, okay, so I want to do formal charges, and here are 2 possible ways to do the dot structure for hydrocyanic acid. So again, formal charge is equal to the number of VE valence electrons minus the number of assigned electrons. So that's how you figure out formal charge, okay? So for this one, I've got H, C, and N. Over here, I've got H, C, and N. Okay, so for the H, for valence electrons, H has 1. And the assigned electrons, if there's a bond, every bond counts as 1. So that would be 1. So it has 1 bond, so 1 assigned electron, so 0. Okay, carbon. So valence electrons for carbon is 4. And the number of assigned electrons, again, there's one assigned electron for every bond. So there's 1, 2, 3, 4. So again, 1, 2, so in a triple bond, there's 3 assigned electrons. Okay, nitrogen has 5 valence electrons. And a non-bonded pair like that counts as 2. Okay, so there's 1, 2, and then every bond counts as 1. So 1, 2, 3, so there's 5. So this is probably likely, because when formal charges are 0, the more likely that is the correct structure. Okay, and then here, so over here, so again, I have 1 valence electron and 1 bond. So for hydrogen, so its assigned electrons are 0. For carbon, notice how I wrote this one, HNC. So I've got 4 valence electrons, and here I've got 1, 2, and then 3, 4, 5. It's not as likely to occur because it's not 0. And then nitrogen has 5 valence electrons, and here it has 1, 2, 3, 4. Every bond is 1. So what the formal charges, that's how I determine formal charges, and then the ones that are 0 are the more likely structures. So this is of these two possibilities, this then is probably the structure. Okay, last thing here, and this is something so for you guys to try, if real quick, and I know I'm over time, so this will be 1 minute or less. But if I go back to my notes, oops. Oh gosh, I screwed it up. Okay, so anyways, back here, if you look here, right up here, here are 2 possibilities. And this is for CH2O. So here's one possibility, here's another. So you guys can try those formal charges. Tomorrow is probably going to be mainly the lab, but if we have a chance, I'm going to come back and do those. So if you look there, you can try that. And in the notes, I think there's a problem. You can try it, problem number 77. You can try that one too. So, okay, I'm going to stop there. Sorry I went over. I will see you guys tomorrow at 10:10. Any questions? All right. See you guys. Have a good day.
Thank you.
Have a good one.
Mr. Wood.
Yes.